Great. Okay, well, good evening. It gives me great pleasure in my role as Dean of the Faculty of Science this evening to welcome you to this inaugural professorial lecture for Professor James Hammond. Before I hand over to James, I'd like to say a few words to introduce him. I'm sure many of you know him and know his work, and know that his work focuses on seismology and the use of seismology to image the interior of the Earth. So James completed his PhD in 2007 at the School of Earth and Environment in the University of Leeds. He then took up postdocs initially at Bristol and then Imperial before settling at Birkbeck in 2015. So now marks 10 years here. He was promoted to professor in 2022, which means that tonight's inaugural lecture is well overdue. We had a bit of a hiatus due to COVID and are sort of catching up with some of the inaugural lectures that we missed then. So it's great to have James now back. James's work in science is complemented, though, by his work in science diplomacy, his service to the community, and also his public engagement. He is particularly well known, especially to me, for his work in establishing the Mount Pictou Research Centre, a centre which focuses on a volcano that straddles the border between the Democratic People's Republic of Korea and China. So in working with scientists from DPRK, James and his colleagues have used science to build trust and understanding between communities with diametrically opposed political systems, something which I think is really critical in today's modern world. But James has also served key administrative roles in the Royal Astronomical Society, and the British Geophysical Association, amongst several others. Turning towards public engagement, James has been interviewed on BBC Radio 4, as well as by several UK and US print media outlets, and he's also contributed to a Netflix documentary on volcanoes. So a very great deal of experience in public speaking as well and public engagement. Given this background, I'm sure like me, you will be really looking forward to something of a treat this evening with James's inaugural lecture. So now let me hand over to Professor James Hammond of the School of Natural Sciences at Birkbeck. Thank you.
Thank you. Thanks, Rick. Yeah, thanks, Rick. Yeah, no pressure, I guess. I'm really kind of blown away for you all kind of turning up, colleagues, friends, family that have come to see me tonight or see this talk tonight. It's a bit of a funny thing giving an inaugural lecture, right? Kind of looking back over 20 years of research, and I like to feel I'm at the halfway point of my career, right? This is not the end point at all. But it's really special to be here and to give this because, you know, I'm first generation going to university in my family. I'd never met anyone who had a PhD before I got to university, right? It was not on my radar at all. I went to university with the aspiration to become a teacher, so I guess that kind of worked out in some way. And it wasn't until I met my then PhD supervisor when he basically tried to get me to do a PhD that it was even kind of a thought in my mind. You know, and he said to me, you know, PhD involves spending 2 months in the Seychelles, and I thought about it for a millisecond, and I thought, well, you know, that seems like a good way of putting off getting a job for a few years, and 20 years later, here I am still putting off getting a job, right? So, you know, so it's really kind of special that I'm here giving a professorial talk. It means a lot to me. And it means a lot that I'm doing that at Birkbeck, right? Because Birkbeck is a place that recognizes people don't always have the aspiration to meet their full potential until later on in life. They don't realize what opportunities are there, right? And Birkbeck is all about that, you know, giving people that chance no matter what stage of life they're at. And so this talk is a little bit reflective, a little bit talking about my path, how I got to where I am. It's going to have a kind of common thread running through it of seismology, because that's what I am, right? I'm a seismologist. I use earthquake energy to image inside the Earth. And then we'll talk a little bit about where my research is going. Now, a little bit of help from Microsoft Copilot. I kind of put this together, which is a word cloud of all my co-authors, right, over the last 20 years. And just to emphasize the point that, you know, what we do, we don't do in isolation, right? You know, there's a huge number of people that have supported me to get here. Some names are bigger than others, right? You know, it gives you a reflection on how crucial they've been to my career. I could spend the whole hour just thanking people, right? That would be a bit self-indulgent. I know this is an inaugural lecture, so you're allowed to be a little bit self-indulgent, but I thought there are a couple of people that I really would like to pick out from this list. The first up here is Mike Kendall. Here we are eating some spaghetti in Eritrea. I think that's how the Italians eat pasta, right? Yeah. Mike was my PhD advisor. I've known him now. He's actually my undergrad, one of my lecturers at undergrad. Known him for about 25 years, one of my best friends, and a big mentor. And then at the bottom here is Clive Oppenheimer, who I met a little bit later on in life, about 15 years ago. And again, we've worked together a lot. And, you know, academia is full of incredible highs, right? Like tonight. Right, publishing papers, things like that. It's full of some pretty lows as well, some low points, right? It can be difficult. And so having a support network, having a family who helps me through those darker points and there to celebrate the good points is important. But having these guys has been incredibly important as well, right? They're the first people I pick up the phone to if I need career advice, for example. Then I'd like to thank all of this lot here, which is the PhD students, postdocs that I've been lucky enough to work with over the time, right? And a lot of the work I'll present is work that these people have done, right? And it's their enthusiasm and drive that kind of keeps me going and actually keeps me current in terms of what is actually happening. So a huge thanks to those. And you'll see lots of faces popping up. I'm not going to name check everyone, but just that's my way of giving thanks to people as we go forward. Okay, so let's get on with the talk. So I'm a seismologist, right? And let's think a little bit about what seismology is. So I need a volunteer from the audience. Ah, we have one down here. Perfect, perfect. Right, up you come. We've never met before. All right, Ben, do you want to assume your position? Okay, so Ben is just going to go stand over here. And what you can see, right, what you can see up here, this is a seismogram, right? This is seismic waves traveling. It's measuring the ground motion on the stage here, right? And you can see there's a little bit of vibration. It's because the ground is always oscillating a little bit especially in London where it's a bit noisy. Right, Ben, what I want you to do is jump as big and as loud as you can. Right, so there you can see, right, Ben has created some seismic energy, right? And that energy has traveled through the floorboards to the seismometer, it's actually my phone, which is sitting under the table here, right? So Ben, do you want to do that one more time? There we go, right? And what's happening is as that seismic energy is traveling, it's deforming the floorboards or whatever this stage is made of, right? It's compressing it, it's shearing it, right, in an elastic fashion. And the speed that wave travels at is determined by what these floorboards are made of. All right, I think we're good now. Let's give Ben a round of applause. Thanks, Ben. And so this is really important, right? Because it gives us a tool that's directly interacting with the material that it's traveling through. Right? And if it's stiffer, right, then it will travel fast. If it's a bit softer, it will travel slower. So it gives us a tool that we have to directly interact and image with the interior of our planet. Here's another example of seismology and how useful it can be. So this is what I'm going to show you here. This is the continental USA. Each one of these circles is a seismometer, right? That's been a part of a kind of permanent network in America. If you see it as a blue color, that means the ground is going down. If it's a red color, you'll see the ground is going up. And I'm going to play this little video which shows all of these seismometers in the moments following the Kamchatka earthquake that happened earlier this year, magnitude 8.8 earthquake. And when you first look at it, you'll see that the colors are kind of random, right? This is just the background noise happening. And then you'll soon see that we're getting this coherent energy that's traveling all the way across the United States. All right, so here we can start to see some energy in a coherent fashion, right? And now you can really start to see these seismic waves, right? You get the impression of this energy traveling all the way across the United States of America, right? And the speed that that's traveling at is determined by what those rocks are made of. So our jobs as seismologists is to look at this, to study all of these waveforms, and therefore infer something about what the Earth is made of. Right? And we normally do that by deploying seismometers around the world. So here we see a cut through of the Earth. Each one of these wiggles here would be from a seismometer. And you can see that these lines over here, you see over here, are representative of the paths that the energy is taking through. And so it's the one way we have of directly probing and investigating the interior of our Earth. We have no other way of sampling, for example, the core or the bottom of the mantle or other things, right? So it's an incredibly useful tool on Earth and now on other planets as well, right? We've got seismometers, I say the royal we, I haven't done this, seismometers on Mars, the moon, and hopefully other places soon. Now, this is really useful, right? Because if we have enough sources of energy, whether that's Ben jumping on the stage or whether that's an earthquake or an explosion, we can look at how long it takes for that energy to travel from that source to our seismometers, right? And that should tell us about something about what it's made of. This nice little cartoon here is showing, for example, this red region is showing a low velocity anomaly. It's a cartoon of a volcano, right? It might be a magma chamber, something like this. It's soft in a magma chamber, it's hot, right? Seismic waves travel slower. So any paths that go through this region will arrive later than we might expect, right? And if, just like a doctor fires X-rays through your body, if they have enough sources and enough sensors, they can build up a 3D image of what the inside of your body looks like. So if we have enough earthquakes and if we have enough seismometers, we can build up a 3D image of what the inside of a volcano looks like, or what the inside of a whole planet looks like. Right? And this modern seismology really kind of kicked off in the 60s and 70s when there was a ban on atmospheric testing of nuclear weapons. And so all the nuclear tests moved underground. And so then there was a sudden need to have a global seismic network that could locate and quantify the size of people's nuclear tests, make sure they weren't doing anything that was outside of the Test Ban Treaty Organization, right? And so we had all this data that seismologists could get hold of, and we have all these beautiful sources, which are earthquakes that are happening all the time, right? And this is a bit of a dilemma for seismologists. You know, earthquakes are destructive. You know, we work on understanding their hazards. They're also our one form of data that allows us to probe deep, deep into the Earth. And so using this combination of earthquakes and seismometers, we can build images like this. Again, it's not my work. This is from a model called S40RTS, right? The green lines are showing the major plate boundaries. And you can see under these in the oceans, they're red. It means they're slow, right? The seismic waves travel slower in these regions. This is all the mid-ocean ridges. They're hot. There's lots of volcanoes. There's lots of molten rock. And then under the blue regions, these are the cratons. This is the thick, 200-kilometer thick lithosphere that's cold, it's dense, and therefore seismic waves travel fast. And this is amazing, right? This is a snapshot of what our Earth looks like at a depth of 100 kilometers, right? It's pretty cool stuff. you know, and that's because that's all based on our X-ray image using our seismic waves and seismology. Now, where I come in is I like to use these methods, but I like to go to interesting places tectonically, geologically, and in every other way to try and do the same methods, but study them in much more detail. And what I mean by that, right, here I've zoomed in on part of East Africa. This is Ethiopia, kind of Ethiopia down here, Eritrea, Djibouti, there's a little bit of Somalia kicking in here. Right, this is a place that I've worked a lot. I'll come back to this and talk to it a bit more. And this is that same tomographic model that I just showed. This is the global tomographic model, S40RTS. And the only two seismometers they use to create this are in these blue stars here, right? This is part of the global seismic network in Djibouti and Ethiopia. And you can see what it shows us is that there's a lot of slow velocities beneath Ethiopia, right? Again, it's hot, it's molten, but there's not much resolution. Right? We haven't got a very detailed image. And that's because, like your doctor, if they only had one X-ray and one sensor, you wouldn't get a very sharp image of the inside of your body. So what I like to do is I like to go out into the fields and put lots of seismometers in a place that is geologically interesting, right? Whether that's Ethiopia, whether it's the Seychelles, whether it's North Korea, Chile, wherever it may be. That's basically where I'm happiest, right? Is digging holes and putting seismometers in the ground. And what this means, each one of these white squares here would be a seismometer, about half of those that I've been involved in deploying. And it means we can go from an image that looks like this to an image that looks like this, right? A much more sharper, detailed image of what the velocity structure is beneath, in this case, Ethiopia, right? And you can see these images are consistent, right? But here now we're showing at the same depth that most of the low velocities kind of following this trend here. This is the main Ethiopian rift with the continents breaking apart up into the Afar Triple Junction where it meets the Red Sea Rift coming up here. And I'll come back to this slide a little bit later on. But just that gives a kind of in a nutshell what my research has been about over the last sort of 20 years. Now, I started my research, as I said, working in the Seychelles on my PhD. And this was really my introduction into seismology, into how useful it can be in terms of imaging the Earth. Even though my motivations, I am going to be honest with you, were spending 2 months in the Seychelles when I first took that on. And the reason we went to the Seychelles, though, wasn't just because it's this tropical paradise. It was because it plays a really crucial role in the formation of the Indian Ocean. So this is a little animation showing the last 250 million years of plate tectonics in this region. Right? And it's the breakup of Pangaea, Gondwana. Right? So you've got Africa here, India, Antarctica, Australia. And you can see about 200 or so million years ago, India, Antarctica, Australia start to move away, rift away, break up from Africa. About 120 million years or so, India starts to move northwards. It starts to break up from Madagascar here. And then this is the Seychelles just going up there. And then for some reason, about 65 million years ago, the rift jumped from between Madagascar to between the Seychelles. And it shaved off this tiny little slither of continental material that's left sitting in the middle of the Indian Ocean today. It's why you get these spectacular granite outcrops sitting in the Indian Ocean, these beautiful white sands and everything, right? So it's a little key marker sitting in the middle of the Indian Ocean that really is a bit anomalous and it shouldn't be there. So we wanted to go and study this and say, what can it tell us about the processes of breakup, of how continents break apart? So I went and we deployed a lot of these seismometers across a number of the islands. And the main method we used here was a seismic method called receiver functions. Now, this method takes earthquakes that happen all over the world. They travel down through the Earth's mantle, and they arrive at our seismic station where we've got this big red triangle up here. And if there's some structure beneath our seismic station, right, as the energy first arrives at our station, some of that energy will interact with that structure. It will bounce around, it will convert from one type of seismic energy to another. And what we do in receiver functions is we try to isolate that energy. I've got laser pointer. Right, we try and isolate that energy to pull out these signals which are related to something about the structure beneath our seismic station. And it allows us, this is just data from one station, it allows us to produce a model that looks like this. This is our seismic velocity, how fast seismic waves travel as a function of depth. Right? These are our receiver functions at the bottom, right? And our job as seismologists is to interpret and understand each one of these little bumps and wiggles in the data. The blue line here shows what you would expect to see for kind of a normal lithosphere, right? This is a normal tectonic plate, the average for the whole Earth. And what we found on the Seychelles, even though nothing much is happening there today, is actually it's very low velocity. And it's got quite a complicated structure within the mantle. And this all pointed to the idea that we were looking at some sort of residual melts, some residual signature of large-scale volcanism that had happened a long time ago. Right? So my thesis was called The Architecture of a Microcontinent, right? And it was how this little continent looks going down into the mantle. So we see all this evidence of magmatic activity, but that must have happened a long, long time ago. And what we relate this to was a huge outpouring, one of the biggest in Earth's history, what we call a large igneous province that happened about 65 million years ago that formed something called the Deccan Traps. So you had a big mantle plume. This is a region of anomalously hot Earth that's rising up from deep in the Earth, and it causes the rocks to melt and erupt at the surface. And you can see the Seychelles was here, right? Sitting just next to India during this time of the Deccan Traps formation, just on the edge of what we think of the expression of this mantle plume. And so what we think has happened is this plume has come up, it's melted the rocks, it's weakened that lithosphere to such an extent that rifting then jumped from down here to start rifting on the Gop Rift between the Deccan Traps and the Seychelles, and cast adrift this small little slither of microcontinent in the Indian Ocean. Right? And it just shows, basically was showing the importance of volcanism in allowing continents to break apart. So I was coming towards the end of my PhD, and again thinking, well, what shall I do next? And it's one of those things that kind of opportunities just jump out and you kind of have to grab them with both hands when they do. Right? And so I went from the Seychelles, where we were studying the breakup of continents that happened 65 million years ago. And I suddenly got this opportunity to go to the East Africa Rift to study the breakup of a continent that is happening today. Right? So to learn those lessons and make those comparisons between what was going on in the Seychelles and what's happening in the East Africa Rift. And this is an incredible part of the world, culturally, historically, and geologically. I think there's nowhere better, right? You've got the East Africa Rift coming up here, where the Nubian Plate and the Somalian Plate are pulling apart. In a few tens of millions of years, we might have a new ocean forming between the two. You've got the Red Sea Rift, where it jumps in on land. You've got the Gulf of Aden Rift that jump on land, and they all meet in this part called the Afar Triple Junction, right? Where the Earth is breaking and pulling itself apart. Now, I got involved in this because of this guy here. This is Professor Atalay Ayeli from the Addis Ababa University. And in September 2005, he was monitoring earthquakes in Addis Ababa and at that time they had this beautiful paper drum roll recording the earthquakes. And he noticed that things were going a little bit crazy, right? This is a normal day of seismicity at Addis Ababa. This is what they were recording on the 24th of September 2005. And they quickly realized that in a part of Ethiopia called Afar, there was a huge seismic crisis going on, right? Over 3 weeks, hundreds of earthquakes. And it turned out that a 60-kilometer long sheet of magma, which we call a dike, was being injected into the crust, right? Causing all of these earthquakes. It caused a small eruption at the northern end of the dike. And it was an incredible kind of once in a generation kind of event, which normally we only see happening in mid-ocean ridges beneath the sea. And we were capturing this on land. So Attlee and Cindy Ebinger here, they led a quick rapid response team. They worked with the Ethiopian military. They got hold of these helicopters. They loaded it with seismometers. They flew out to this part of the region, deployed the seismometers, collected a load of samples, collected eyewitness reports and the like, you know, in a really kind of exciting event. And then I bumped into Cindy at AGU in San Francisco, and she was telling me about this. I was talking about my research. And she said to me, oh, do you know what? We need someone to go to Afar to service and download all the data from these seismometers. Would you be interested? Thought about it for a millisecond again, and I thought, yeah, that sounds exactly the kind of thing I would like to do. She said, there's one catch. We can't get the helicopter anymore. So you're going to have to find another way of getting into the middle of the Afar desert. So we went to the Afar, and we met with, this is the chief of Teru, Mohammed, and his village elders. And we met with them, and they lent us some camels for the trip. And we spent a week trekking out into the Afar desert, where we could see the evidence of these earthquakes, right? So this is deformation associated with the earthquakes and the extension that was happening in the region. And we downloaded all the data from the seismometers that we could get to, right? An incredible experience. And it basically meant that when all of these universities internationally and all of these funders got together to say, like, this is a once in a lifetime opportunity to study these processes, they generously wrote me into their NERC grant, and I got a 5-year postdoc, would you believe? Anyone in the know is, like, you know, unheard of. And so I had the pleasure of working at the University of Bristol on this project. And again, huge cast of people that did work on this and continue to work on these data today. So my role was to kind of look after the seismic array in this part of the world. So this was the seismometers that had been deployed when I first got involved. And then all of these blue symbols here and black symbols and even the red ones in Eritrea, these are the stations that I had a hand in and basically had to look after over 5 years. And I probably spent, I don't know, 6-7 months of that 5 years living with the Afar out in Ethiopia. Incredible, incredible experience. Here's just a few pictures because I can't resist. This is, this kind of testifies why it's such a unique place. These are like a hydrothermal sulfur springs in Danakil. These are the kind of things you might expect to see on a mid-ocean ridge in a system. You've got Erta-Ale lava lake. This has been erupting constantly for decades. Right? Again, exactly the kind of things you might see on a mid-ocean ridge. Up in the highlands of Ethiopia, you've got the Lalibela. This is carved out of volcanic tuff, right? Rocks that they've carved churches, right? Showing again volcanism up here, tens of millions of years old when the rifting process started. And then the work in Nabro volcano, one of the most difficult but rewarding field work that we've got to do. I'll come back to that a little bit later. Now, what I wanted to do, the first task, a part of this project, was again going back to receiver functions using some of the methods I'd learned in my PhD to produce a map of the crustal thickness across the whole of Ethiopia. Right, so here, what we're showing here, this is Ethiopia, Djibouti, Eritrea. Right, these black lines here show the edges of the rift. And what we see is this is really thick crust, about 40-kilometer thick crust that sits on the margins of Ethiopia. This is basically the old kind of continent. And then as you rift it apart and the Red Sea rift comes in here, we get down to about 16-kilometer thick crust, right? So as the rifting process happens, it stretches that crust, it gets thinner. But actually what we found, this wasn't as thin as we expect it to see, which shows lots of magmatic addition into the crust itself. And we also saw these little regions of thicker crust sitting in the middle of the Afar region. And this is quite neat because like the work we did in the Seychelles, what we were finding was as Arabia and this little microplate here, Danakil, are moving as the whole rifting process takes place, the triple junction migrates its way up here. And as the rift has to reorganize itself, it's shaving off little slithers of continental crust, right? Just like we were seeing in the Seychelles 65 million years ago, that process is happening in Afar today. And we're forming little microcontinents that will one day be isolated within whatever this ocean ends up being called in 10 million years' time, right? And so those same processes are happening, and it shows this kind of magmatic rifting can weaken the lithosphere to such an extent that it can isolate these little slithers of continental crust as it does so, right? And allows for these complex breakup histories to occur. Now, the other thing that I worked a lot on was seismic tomography, right? So we've shown this image already. We've got this beautiful expression of the rift in the mantle here at a depth of 75 kilometers, right? This is where all the melt is stored that eventually works its way up and erupts at the surface. And this compares beautifully with the kind of images you would see looking at mid-ocean ridges. But we didn't want to stop here by, with these squares here, the seismometers we deployed in this region. We wanted to take this a little bit further. And we realized that because this is such an interesting part geologically, so many groups over the years have deployed lots and lots of seismometers across the whole of the East African Rift. And so as part of my NERC fellowship, I'm working with my very first PhD student, Chiara Siviero. We took data from the whole, as much data as we could get hold of to produce much bigger tomographic inversions. And what we show here, we can now look much deeper into the Earth. This is going down to about 800 kilometers depth into the Earth. This is a slice at 500 kilometers, and we see these kind of low velocities that are coming up through what we call the transition zone in the mantle, which are little isolated upwellings of hot material that are coming up through this system. So we have low velocities, melt-filled region in the kind of top 200 kilometers, and then these little things poking up through the transition zone, which are feeding this whole system. And it's giving us this sense of the dynamic nature of this process, right? Hot materials upwelling from deep in the Earth, driving this whole rifting process. And so this is a little cartoon that Chiara put together, right? There's some deep source of heat coming through, and then we get these small little upwellings that are coming through, feeding the rift system at the top here. And this feeds into a whole bunch of imaging models, all of which show evidence for significant amounts of melt sitting in the Afar region, right? And one of the things that drives my research now is trying to take these images, all these red regions, which we think are hot, which we think might be molten, right? And how can we take those and give you a quantitative estimate of maybe how much melt there is, or how that melt is distributed, right? It's one thing a seismologist saying, oh, look, there's lots of melt beneath all these volcanoes. Well, the petrologist says, well, yeah, right, there's volcanoes, right? That's not a surprise. What we want to know is how much there is, or how mobile it is, right? And that's the challenge we have as seismologists, because we, at the moment, can't relate very well. We don't understand the relationship between melt and velocities because it's dependent on the shape, the distribution, and the amount of melt there is. So Lauren Cox, who's just passed her Viva for her PhD, and Dominic Ryan, 2 PhD students who've been working on this, trying to unravel that a little bit. But that's a talk for another day. The next stage in my career, and something that really opened up a whole new avenue for me, was my desire, right? So when I was working up in AFA, my desire was to push these seismometers as far north as possible. Right? And so we pushed all the way up through here in Ethiopia, right up to the border until we got to the border with Eritrea. And Ethiopia and Eritrea at the time were at war with each other, right? So this was a border that you couldn't cross. You couldn't get from one side to the other. You couldn't even fly from Ethiopia to Eritrea. There was no diplomatic relations. But the geology never stopped, right? And we wanted to look at that last little slither of continental breakup, which is happening up here in the Gulf of Zula in Eritrea. So I remember I was having a coffee or a buna with Atale in Addis Ababa. And I said, well, it'd be great if we could put some stations in Eritrea. And he said, oh, my old professor now works at the Eritrea Institute of Technology. I could put you in touch with him if you want. Said, okay, that would be good. So I got in touch with Gebra Bahan Ogabazi, and we had this discussion, and he was really keen, and we started to develop a memorandum of understanding between Eritrea and the University of Bristol that would allow us to put the very first seismic network across Eritrea, right? Quite excited about this. And then the UK and US put sanctions on Eritrea for one reason that I can't quite remember why now. And he wrote to me and he said, I'm really sorry, but the Eritrean government will do nothing with the UK right now because the sanctions are in place. About 6 months later, I got back in touch to see if anything had changed. And he said to me, oh, there's a conference on mining that's going to happen in Asmara. You should come and speak at that. I said, well, I don't know anything about mining. He said, oh, that's fine. I'll get you a slot and you can present the project. The whole government will be there. So, okay. So as a 28-year-old, off I hopped to Eritrea and I did. And I presented this what we wanted to do, that we wanted to deploy the first seismic network. It would help with hazards. Maybe it would help with mining. Right? I mean, it was a bit of a stretch, but and they agreed. They said, yeah, you could come. And so I went in June 2011 with my 6 seismometers to deploy this first network. And we were all ready to go. And Gebra Bahan came to me and he said, your permission to travel has been refused, has been rescinded. You're not allowed to leave the capital city. You can't go anywhere. I don't know what's happened. And so we never quite worked out the story. I can give you some ideas over a beer later or something. But basically, it looked like I'd have to go home with all of my equipment and we weren't going to be able to deploy our seismometers. And then this happened. Right? And this is Nabro volcano. It's sitting on the border. It's about 10 kilometers away from the border of Ethiopia in Eritrea. And it's a volcano that's never erupted in human history. Last eruption, I think, was about 20,000 years ago. And suddenly it erupted with no warning. And I'm sitting in Asmara. And in fact, the only warning came as I was sitting in Asmara, checking my email, and I got an earthquake alert from the USGS saying, oh, there's been an earthquake in Eritrea. That's a bit odd. So I phoned up Gebra Bahan and he phoned up the local administrators and they said, yeah, there's been lots of earthquakes, and they evacuated communities that were living in this caldera. And there were fatalities, unfortunately, but they saved a lot of people by evacuating that caldera. But this volcano erupted and I had a bunch of seismometers in Asmara. Right? So we had the equipment that we could use to try and monitor this and understand what's going on. And I still wasn't allowed to travel, but I was allowed to train the Eritreans on how to use our equipment so that they could then go and deploy Eritrea's first seismic network, which is what they did. And then we spent a little bit more time with the Eritrean government, and then myself, and this is Clive up here, were granted permission to go and visit the volcano. And as far as we're aware, We're certainly the only international team to go to the volcano. I think we're the only international people that have been in this area of the southern Red Sea region of Eritrea. Right? And it was a really incredible experience. This Berhe Goitom, who led the deployment of the seismic network on the volcano, we put a whole bunch more seismometers on. And he came to do a PhD with us eventually in Bristol. And this is our field team from the Department of Energy and Mines, Eritrea Institute of Technology, the Geological Survey, and we had a military escort because we were quite close to the border. It's an incredible experience, incredibly rich data set that we gathered here. And this is another example of how seismologists can use this seismic energy to understand processes in the earth, because here what we wanted to do was locate all of the earthquakes. Right? You know, when an earthquake happens, you can feel it, but you don't inherently know where it happened, right? Or when it happened. But if we have enough seismometers, we can essentially triangulate the position and the time of where that earthquake happened. And we quickly realized when Berhe and Joe Hamlin, two PhD students working on this, quickly realized there was a lot of data here, right? And they were hand-picking all of these signals. And after a few months, Joe had picked 658 earthquakes in about a 38-day period. This is what's plotted here. And it started to highlight some of the features that are going beneath the volcano. I think the magma chambers in this region where we don't see any earthquakes because it's too hot and too mushy and it can deform too easily. We can see a conduit coming up here to the surface where the lava flow came out of. We saw actually seismic activity on nearby volcanoes as well. But then a little while later, this guy, Sasha Lapins, took it on himself to think, hang on, we could do this by machine learning. Right? You know, that's what we do, everything by machine learning. Well, at least we do this. And Sasha developed some machine learning algorithms. In 4 hours, he ended up picking 31,387 earthquakes over the whole 14-month period, right? And I think this is really, as we go to large data sets, this is really exciting development. It's allowing us to do a lot more and to focus on a lot more of the processes. And again, you can see these beautiful features, like these conduit features coming up here. And this is work that's being continued now by Abigail, who's sitting in the audience just there, where Abigail has extended this to get even more earthquakes, 48,000 earthquakes by tweaking the algorithms a little bit. But what I think is really neat is also extending the training catalog so we can look for volcanic earthquakes. These are long period earthquakes associated with fluid movement. And here you can see it beautifully lighting up just where we think the conduit is, just where we think the lava is moving as it comes to the surface. Right? And so we're now pulling apart this to see what signals we can have. Right? So I think machine learning is an aspect that we're going to hear a lot more about in seismology as we go forward. Now, the other reason why this was such a big moment in my career was one, it got me introduced to Clive, and it got me introduced to the idea that you need a little bit of diplomacy if you want to work in certain parts of the world. Right? And so when Clive got a phone call from a colleague in Beijing saying, some North Koreans have reached out to me and they said they want some volcanologists to come to Pyongyang and meet with them. Do you know anyone who would be interested? Clive was like, yeah, I've been working with a guy who might be useful in this context. So he phoned me up and he's like, James, do you want to come to Pyongyang in a couple of weeks? And again, I thought for about a millisecond and I said to myself, yep, that definitely sounds like something I would like to do. And so myself and Clive, we traveled to Pyongyang to this magnificent and incredible volcano that sits on the border of North Korea and China. When I say the border runs through this caldera lake, right? So about 2/3 of the volcanoes in China, 1/3 of it is in North Korea. It's a real kind of incredible place. It's responsible for one of the biggest eruptions in human history in the year 946, bigger than Krakatoa, right? A bit smaller than Tambora, right? So this is a big volcano sitting in a rather complicated part of the world. So here's Clive and I arriving near the volcano. This is our Air Koryo flight that we actually chartered the whole plane. There was no flight to get there, so we had to pay for the whole plane. We filled it full of North Korean scientists, and we flew up to the volcano. And the reason why the Koreans were so concerned about this was that the volcano had been showing signs of life. Right? So it's a big volcano. And from about 2002 to 2006, there was an increase in earthquakes, just like we were seeing on Nabro. There was volcanic gases being emitted. There was ground deformation, all pointed to magma moving and recharging beneath this system. Caused a lot of consternation across the Korean peninsula, a lot of attention in China, and the DPRK, the North Korean scientists were equally concerned. So we went up there, we were taken around. This is some of the pumice deposits from that 946 eruption. We learned about the monitoring efforts that the Korean scientists were doing. We went out onto the lake to visit some of the hot springs. But really what the highlight was, at the heart of it was a bunch of scientists coming together, sitting together, and really exploring what we could do to work to understand this volcano in more detail. We learned about the decades of research the Koreans had been doing. We talked about what we were doing on other volcanic systems around the world. And we had a whole bunch of just really fundamental questions that we wanted to work on. Everything, we don't even know why the volcano's there, right? It's not on a plate boundary. It's a weird volcano. It's what we call an intraplate volcano, right? So we thought, we can work together to really address some of these. We don't know what its history is, right? And that's our only clue to what it might do in the future. We don't know what the state of the volcano is, and that's what I'll talk a bit about here. And all this feeds into understanding what risks a future eruption might pose to the local, regional, and wider populations. So we went away and we managed to build and sustain a 14-year collaboration working with the North Koreans. Huge bunch of, lots of scientists involved from China, from America, from the UK, as well as from North Korea. And then people over here, which I kind of put into the diplomacy bracket, who've been equally as important as holding all of this together. We've got Norm Neureiter and Rich Stone from AAAS, the American Association of Advancement of Science. Got Sir Martin Polyakov and Sir Richard Catlow, former foreign secretaries of the Royal Society, who led a lot of the engagement work with the government and signed agreements on our behalf. You've got Cosimo in Beijing, Kumran in Pyongyang, who've really helped bridge the links between the different parties. I can't thank all these people enough. But what I like to do is dig holes, right, and put seismometers in the ground. So that's what we went and did in North Korea. We deployed a seismic array for 2 years in North Korea. We put 6 seismometers. This is one of our holes. Right? It's concrete-lined little bunker, part of this potato field in the village of Sinmusong. And you can see our seismometer would go in here. We've got a little GPS antenna for timing. You can see our solar panels on the roof of this person's house. And then this little wire going in is our batteries, and everything is inside there. Right? And that family would look after our seismometer for 2 years. And that was really important because this is the weather it's like in August. This is what it was like in October, right? And I had to go once in October. We had to climb the volcano through the snow because the roads were impassable. It was already minus 10 degrees at that time, I think. Place. Yet they looked after our seismometers throughout that time and got us some really nice data. So what did we do with that data? Well, the first thing, as is always the way, we went to the receiver functions, right? And we can map out the crustal thickness again, right? So these are our 6 seismometers, and we added in some data from China as well. Right? And what we see is a thicker crust beneath the volcano. And then what I'm showing here is we call this a VPVS ratio. It's a ratio of two different types of seismic velocities. If it's high, above 1.9, it normally tells us that's where fluids are in the crust, right? Where melt might be present. And you can see bullseye right beneath the volcano, we have high VPVS. It was our first indicator really that we definitely have molten material sitting beneath this volcano today. This is a receiver function cross section. It's a bit of a funny plot to look at if you're not used to looking at these things. Basically, each one of these wiggles is if you see a black peak in these wiggles here, it's showing us that there's a sharp jump in velocity at that depth, right? So this is showing us the crust into the mantle. And you can see we get this thicker crust directly beneath the volcano here. But what was quite interesting was these gray peaks here, which show the opposite. That shows as you go deeper into the earth, the speed that the seismic wave travels gets slower. And that's not usual, right? We don't normally expect that. And so we think this is showing us the top of a magma chamber. This is showing us the top of where magma is stored beneath this volcano today. So this was quite a neat result, right? It's showing us that we think there's magma sitting beneath this volcano today. But we thought we could do better than that, right? We could go beyond just deploying our 6 seismometers. These are the 6 seismometers, these blue triangles here. And so we had some big meetings in Pyongyang. We brought about a dozen international scientists together with North Korean scientists, Chinese scientists, and we planned out this kind of cross-border deployment of seismometers in China and in North Korea. So we, for the first time, could produce images of the whole volcanic system. The plan was to deploy about 40 seismometers in China, led by the China Earthquake Administration. We would work with the Earthquake Administration of DPRK to deploy seismometers in North Korea. We got the funding in about July 2019. We have to get licenses from the UK government, the US government, UN Security Council to allow us to do our work. We got those in about December 2019. We were all ready to go for our big field campaign in the summer of 2020. And you all know what happened next, right? COVID got in the way. And so we still have funding, we still have the instruments, we still have everything ready to go for the DPRK deployment, but travel still hasn't really opened up yet after COVID. But we did manage to get the seismometers into China, right? And so I'm going to show you just a few results from that work, which has been published by Yu Weishan, a PhD student at the CEA earlier this year. Right, and going back to those tomographic images, what Weishan has managed to do is produce really beautiful images of the crust beneath the volcano. We see this evidence for a thicker crust. But what I'm going to focus on are these yellow regions here, which is labeled LV2. Right? These are low velocities sitting exactly where we see that receiver function signal, showing evidence for low velocities at about 10 kilometers depth. And we think this is, we're kind of getting to the point now where we have quite a unified model from many different geophysical data sets that we've got a rather significant magma chamber, magma reservoir sitting in the mid-crust beneath this volcano. And so it's quiet at the moment, but I definitely think this is a volcano that has the potential to erupt, and it's one that deserves our attention. And indeed, the Chinese and the Koreans are monitoring this volcano continuously. That's just a picture of that. So where did we go from here, right? And I think this is now looking a bit forward into the second half of my career and where I think we're going. And I think what I'm really excited about is that there's new technological developments in seismic equipment that are going to present a little bit of a major shift in what we can do with seismology. And everything I've talked about today involves deploying seismometers that look like this, right? So there's a seismometer buried under all these rocks here. This is, again, Nabro in Eritrea. These seismometers cost about 10 to 15,000 pounds each, right? They're not cheap. They require a big car battery to power them, which requires solar panels and GPS antenna. You need a little fence to keep the animals away so they don't nibble all your cables and everything. Goats is the big problem around here. You might need to hire someone to look after it, to make sure that people don't interact too much with the instruments, right? So it's a bit of a logistical, financial burden. And it means we're kind of limited deploying tens of these instruments at any one time. This is Victoria Lane from SAIS UK at the University of Leicester. She's got about 100 seismometers on her back, right? This is one of those seismometers. I have my trusted assistant in the audience who can pass one of these around if you want to have a look at it. Do that, buddy. So this has got power. This has got the seismometer. This has got GPS. It's got everything built into it, right? So it means all we have to do, and we literally do, is drill a hole in the ground, stick this in, and we can deploy hundreds, thousands of these for the same time and cost as it takes to deploy our broadband seismometers. They're not as sensitive, but the scale of it means we can do some pretty cool and new things. And so we are deploying, we can deploy these on volcanoes, we can deploy these in tectonic areas to look at earthquake faults, to aftershock sequences. But one of the things I'm really excited about is using these for brand new applications in environmental seismology. And so actually through Birkbeck RIF funds, so again, very grateful to Birkbeck, we did a deployment up in Dumfries, this is Kevin Davidson's PhD work, where we deployed 1,600 of these in a farmer's field. Right? And we picked this farmer's field because it's got this critical zone observatory in it. And it allows, so in here, they're monitoring soil moisture, temperature, all sorts of things. And we wanted to look and see, well, from seismology, can we actually measure velocity changes that we can associate with some of these environmental conditions in the soil? And if we can, does that give us a brand new way of monitoring over spatial scales that we don't have available at the moment, environmental conditions in what we call the critical zone, where our water is, our roots are, where our food comes from, these kind of things. And, oh yeah, there's a little video just to show that my work is not all glamorous. I am in the lake, see the farmer particularly welcome in his fields. See, spreads his butt everywhere. Yeah, career so far. But the point being is that we think we can, right? So here what I'm showing is at the bottom here is from the Critical Zone Observatory. This is rainfall, right? So millimeters of rainfall and hourly rainfall. In the blue is the volumetric water content. It's basically measuring the soil moisture from a little sensor that sits in the Critical Zone Observatory. And you'll see that when it rains, the soil gets wet. That's not my big message, but it's quite reassuring. But what we also see is that every time it rains, we see a reduction in seismic velocity. Right? And so we're seeing these very small changes in velocity that I think we can associate with soil moisture. And this is cool because we're now looking, with this method, we're not looking at a tiny little point source that's buried 20 centimeters below the ground. We're looking at a volume of soil about 10 by 10 meters cubed. Right? And that opens up a whole new ball game in terms of what we can monitor and what we can understand about the soil. And so we're playing around now with the soil physics, and what we think we can do, if we can constrain it well enough, is we can take our velocity measurements and we can basically convert it into real-time monitoring of water table level. Right? And if you're a farmer, I think that's quite useful information, right? If you want to know when to irrigate your fields or not, or when to put your animals on the field because it's getting too wet. What we noticed here, there's a big flood event, and we can see the water table getting close to the surface in the days leading up to the flood event. Is that a precursory warning that we could use? We want to apply this on landslides where water is a big reason, a trigger for landslide events. Can we monitor water levels in these regions in this way? So this is a really exciting something that was just opening up to us because of this new technology. And please, this is going to keep us busy over the next few years. I just got we got two big grants, a Net Capital grant working with all these institutions where we've just bought 2,000 of these little nodes. We bought 400 of another type of node for use by the UK community to use in all sorts of applications. There's some in Iceland at the moment. There's some going to the Caribbean to look at volcanoes. We're going to apply this to look at environmental seismology. I'm going to take them to Mongolia to look at fault movement, earthquake hazards in Mongolia, for example. And then the other thing I've just got is to actually a Royal Society Industry Fellowship to work with the company that makes these nodes, right? To actually work hand in hand with them to say, these little things which were designed essentially for exploration of oil and gas, how can we apply these in more environmental settings? You know, what do we need to do to make them more applicable in those areas? All right? And this little wheel kind of gives some of the ideas of where we can go. All right, I've noticed the time, so I'm going to just kind of wrap up here and take a bit of a sideways step or a step into something completely different. Because the other thing that where my research is going has moved quite far away from seismology, actually, and it's into this world of science diplomacy Rick mentioned at the beginning. And our work in North Korea has, you know, we went there as scientists, and we still are there as scientists doing a project on a fundamental project studying this volcano. But one of the biggest achievements we have, and I think I've got a slide here, right? This is a slide I put together for a journal called Science and Diplomacy, just reflecting on everything that had happened on the Korean Peninsula over the 14 years that we've been working there, right? And it's been a pretty turbulent time on the Korean Peninsula, whether it's changes of leadership and foreign policy, whether it's nuclear tests, missile launches, joint military exercises, UN sanctions, COVID has been a big challenge. But all through that time, we've managed to get funding, we've managed to get all of our licenses in place, we've managed to meet with our Korean colleagues, we've managed to publish papers with them, right? And as we get into this world that's a little bit more, let's just say, geopolitically complicated, our project is starting to get quite a lot of attention, right? Because it's an example of how science can transcend. It's not separate, nothing's ever separated from politics, right, and national interests, but it gives an opportunity for countries that have very little relationships to work together in areas of mutual interest. So we've just launched the Birkbeck Science Diplomacy Initiative. So big thanks to Matt, who's been helping me here at Birkbeck. We've got colleagues at the Royal Society and UCL. We're going to grow this to try and create a center or a hub here at Birkbeck focused on this area of science diplomacy during geopolitical strain. And, you know, so with this is a comment that came out by myself and Jean-Christophe at UCL just a couple of weeks ago in Nature, where we were reflecting on some of these changes. And I think this figure here, this isn't a figure trying to get across that there's any causation here, but the histogram is showing the number of sanctions that exist at any one time, right? And there's more international sanctions in place at the moment than at any other time in history, right? And, you know, whatever the reason of these, they are barriers to collaboration, right? They're barriers to stop people working together. That's exactly what they're designed to do. At the back here is the warming stripes, right? Showing how our planet is heating up. And I think we're in a position where we're creating more barriers to collaboration at a time when it's more important that we work together to resolve these global challenges, right? Whether it's climate change, pandemics, or a big volcano that sits on the border of North Korea and China. And what we're arguing in this piece is that there are ways to do this. Kind of showed that a little bit with our work in North Korea, but it really requires diplomats, governments, universities, researchers, funders to kind of come together and work out a mechanism by which we do that. We're not saying you can't sanction places, but it's going to have consequences, and we might want to think about how we minimize those going forward. So I'll finish on a positive note and a shameless plug, really. You know, again, working with some Birkbeck funds as well as others, We held this big conference in Mongolia last year, and the whole aim of this was to bring those communities together from countries that maybe don't have the best relationships all the time, to explore those areas of common interest and build collaborations in this area of disaster research. It went really well, so well, we're going to do it again, right, next year. So if anyone's interested, we're at this conference in Mongolia in 2026, and I'd like to see you all there. And I'll finish on that. Thank you very much.